What's up, everybody? Happy Monday. Welcome to Earth Science. Welcome back from February break. I was here this morning, as evidenced by this video, but had to leave for a doctor appointment in the afternoon. What I want to do, most of this work is on your own, but I want to bang through these two quick pages just to put us all back on the same page for glaciers and maybe introduce a few minorly new ideas. And then you'll be off and running. You'll have the rest of the time to work questions and other stuff. So let's start with how these things even form in the first place, which we kind of skipped over, just jumping right into the features. But now that you've seen the results of these glaciations, how do they work? You've basically got an area where there's accumulation. Go ahead and circle that. And if you haven't grabbed a pencil yet, do that and grab this worksheet. Pause if you need to. But there's an area where there's more accumulation, and there's an area where there's more ablation. Now, those terms aren't going to show up. Don't panic about that. But idea-wise, this is the area where there's enough snowfall that there's a net gain in snow, which is really ice, right? Before it melts off, there's more being added by snow than there is in melting. And if it snows, and then it snows, and then it snows, and then it snows, you're going to get compression as you get lower and lower down. It squeezes the air out, it gets harder and harder, and eventually forms ice. As we discussed, that ice can be like malleable. We talked about the video, some people saw it, where like this like compressor takes an ice cube and turns it into a sphere without cracking it. So as it is under the weight of all of this, it can almost kind of flow like a really rigid Play-Doh. As it does it, it's going to scrape up bits of that rock and move them to other places like glacial erratics. It's going to leave scratches like striations. All of the stuff is happening that we talked about. But that would be the area where it's getting bigger. So that giant hole in the ground out that window over there, Lake Ontario, would have been the area where the glacier was like a pancake being added to, getting thicker and thicker. And then as it squeezed down, it spread out, just like how you pour a pancake onto a griddle. Go further south and you're going to get to an area where it's called ablation. And again, don't panic about that vocab. But basically, if we wanted to write down, this is where the glacier grows. And this would be where the glacier shrinks. Excuse me. So get further to the south and you're going to have an area where there's more melting or evaporation than there is addition. There's still ice, but the net gain from year to year is a negative, is a loss. So you lose more and more and more. And eventually you get south enough, which in our case was only down at its furthest advance to like the Pennsylvania state line, and you'll be at the end of it where things start breaking off and melting, and you're down into not glacial area. All right, good so far. There's two basic types. We won't really panic about these either, but what most of New York was covered in was a continental glacier, that pancake idea. If you're up in mountains, present day, you can still see these high in very high mountains where it's flowing down the slides of a mountain. So these, if there's a minor difference, are a little bit faster. We don't need to get too caught up in that, though. I'm going to show you the things we do need to get caught up in. It's definitely here. With these valley ones, a famous study that's been repeated many times is that they climb away the heck up there. They pound in a bunch of metal posts like rebar or something and hang flags on them and then leave and come back. And when they do that, they see that here in the center, it's going the fastest. There's drag introduced by the sides. And this almost exactly mimics what we've already talked about in streams. Remember with streams, the fastest water is towards the middle so that when the river bend curves, that fastest water goes towards the outside because the water doesn't know it's turning. But then it struggles to make its way back towards the center. It's always the center with the least resistance that goes the fastest, both with ice and with water. So they have similar behaviors. It's just this is way, 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 way slower. Right, from 1874 to 1882. That's a long time for it to only move a little bit of distance. So what are some of the big ideas? There were several advances of ice during the Pleistocene and retreats. The ice came and went and came and went and came and went. And this all ended essentially about 10,000 years ago would be when the last melt-off was. And during that time, especially close to Lake Ontario here, and it's crazy to imagine, but the sheet of ice from the present day ground to the top of the glacier was about a mile. Now, most of the landscapes we see in New York, and this is where life gets a little complicated, because as I've said, and as we're going to probably have as a question when we get to the test later this week, hint, hint, by the way, there's a test later this week. This question may be there. So if you had to answer it right now, what would you say? What are the two factors that determine landscapes? If you said bedrock and climate, winter, right? That's still true. That works. But we also happen to live right now, you and I in this high school, live in an area that's so immediately post-glacial that's due to those glaciers coming in and out. I don't know how to make that go away. There we go. Due to those glaciers coming in and out and leaving so recently that the bedrock and climate stuff hasn't really totally taken back over yet. Only 10,000 years ago, these things left. That's like nothing geologically. And in their wake, they've left us a bunch of features. So I'm just going to do like a line here. This is the next section. These features right here, this one and this one, show us, and the Regents likes this, the direction of glacial flow. Yeah? The easy one to picture, most people do pretty well with this, are these scratches in the bedrock. If a glacier is riding over bedrock and it has other boulders embedded in it, as it's slowly grinding its way over, it leaves those scratches. We do have to know the name of them, but people usually do pretty well with that. These are called striations or scratches in bedrock. And the idea that it's parallel is usually a no-brainer for people. Like clearly this glacier was going in this direction. Or maybe the other direction, but at least parallel with them, right? There's little tiny things that trained geologists can look for to know exactly which way. But we rookies, we amateurs, can at least say that, yeah, it's that way. It's clearly not going across those. How would that work? That doesn't make any sense. If the glacier flowed and scratched these, those scratches show the direction the glacier was flowing. All right. U-shaped valleys as well, flow in and out. So the glacier, like the thicker continental glacier, would have plowed its way down and then worked its way back out. Which leads us to this idea that, again, the Regents loves, which is the difference between a V-shaped valley and a U-shaped valley. And it'll come up. There's no way around it. The tighter V-shaped valleys are due to rivers. Sometimes I make a capital V there. Because, hey, if it's a V shape, there's a V in rivers. That'll help you remember, right? Narrower, tighter. I'm going to show you two real-life pictures here in a moment. Whereas the broader, flatter bottomed, steeper sided U-shaped valleys tend to be from glaciers. So you've probably seen these pictures if you were with us during the slideshow, but let's do it again. So this is a perfect textbook U-shaped valley down outside of Tully, New York. So the glacier would have melted its way right down that valley, plowing up material as it went, and then receded its way back out. And the result is that you got the steep-sided drop over here, and then a pretty flat bottom, and then the steep-sided rise over here. And this, again, is where Labrador Mountain is. Where you ski Labrador Mountain, it's not a mountain in any way, shape, or form. It's the side of a glacial valley. Now, if you drive up a little bit here and take a left, kind of in that little notch right there, you can get to a river valley, really with a hanging waterfall. This is the waterfall in winter. Oh, they keep coming over here. Sorry. This is the waterfall in winter. So this would be coming right at the camera, and then behind me is the U-shaped valley. Looking at it this way is a little easier to see the V. Okay. Steep side like that, coming down in a V shape. So the river flowing out into the U-shaped valley. If you can see that ridge over there, there's the far side of the U-shaped valley. So it like curves and the bottom of the valley comes at us, and the wall comes up on this side that we're presently standing on, except the V-shaped notch is in it because that river has eaten away at all that material and taken it away. So that's that. V, like screenshot this in your brain. V-shaped is for rivers, U-shaped is for glaciers. the Regents will hit you up on it. These like hills that have the steep end and the gradual ends are going to happen. They're going to come up. They're called drumlins. Drive around between Oswego and Rochester north of the Thruway. It's drumlin after drumlin after drumlin. There's over 1,000 of them easy. Recognized by the steep slope on the end that the ice came from and the more gradual slope on the other side. So like circle this ice flow thing. That's where we know the ice is flowing. So in the general pattern, these really point towards the lake. For most of the drumlin field, that means they're pointing north. With the guess being that like as the ice pushed its way in this way, it shoved stuff until there was enough resistance that it like flowed. Because again, ice can be malleable under pressure. And then slowly like worked its way down that side until it started pushing stuff again to make the next drumlin down the road. Anywhere, again, go from Oswego to Cato to Weedsport, and you're going to go by dozens and dozens of them. It happens over and over and over again as the drumlin shoved all the sediment around. So we're going to want to know this term right here. Glacial till. Stuff deposited directly from the glacier is made of glacial till. So this is sediments dropped directly from glaciers, right? Moraines, drumlins, things like that, where it got dropped and that's it. Now, I know I showed most of us this, but if I can show one YouTube video on another YouTube video, we'll get meta here. I think this was the good one. No, it's not. Let me pause and find the right one. So this is a very close-up view of glacial till. And if you can put on your geologist lenses, what you're seeing here is mixed particle sizes. There's down to very, very fine clays, silts, sands, pebbles, cobbles, and boulders, all of it. Glaciers are so strong they pick up all of it. When they're done with it, they dump all of it. Now, in the 10,000 years since this thing has been here, it's been raining on them. And all of these little rills are a result of rain washing out some of the sediment. And in turn, sorting it out, organizing it. Running water sorts sediments. But the glaciers, as big and powerful as they are, show up, grab it all, dump it all. Big, violent bulldozer. Slow, but violent. You can see like giant boulders down here. So they can pick up, that thing's like the size of a small car. It can pick up enormous boulders down to the finest clays, but when it's done with them, it dumps all of them. So yeah, that's what glacial till is. That drone shot, all that stuff is glacial till. And the big point is that they are unsorted. Now, sometimes you'll also see unlayered, because running water like leaves stuff, then leaves more stuff, then leaves stuff, tends to leave layers. But the bigger thing is the sorting or organization. Right, so glacial till is the stuff dropped directly from glaciers, and it is unsorted. Anything from running water. So this is where Long Island is cool, which, let's just grab a random map. Long Island has two big moraines up here. So there's two hills running all the way along the length of it. Those are deposited directly from the glacier. They'd be unsorted. But then again, rain on those for like 10,000 years. And the rest, the south half of the island, is from outwash, is from running water coming off of those moraines. And that gives us sorted and layered deposits. All right. This might be the biggest idea. That river versus glacial U-shaped, V-shaped valleys the region likes, but this it loves. It comes up repeatedly. So again, jam that in your noggin. And this is just kind of saying it again. What is glacial till? It's that mixture of different size blocks, stone, sediment, the biggest rocks down to the smallest sediments. So this is kind of like maybe what Long Island would be like. Here's the long terminal moraine. We won't label everything on here, and I appreciate you sticking with me. right? That runs that whole thing. And this diagram is not perfect in some ways, but I really like how back here behind the terminal moraine is that, like, you see how it looks kind of like unsorted. This is their graphical representation of unsorted. Whereas past it in the outwash plain, where running water has done the work, that's where it gets sorted and organized. So this is your outwash plain, sorted, running water, sorts materials. You've been to the beach? You've been in a very sorted environment. The sediments that are there are all about the same size. And yeah, if you go to the ones around here, sometimes there's like patches of all sand and patches of all cobbles or patches of pebbles. But that is organization. That is running water from waves and wind, organizing materials by size, not just all randomly dumped into one pile like the drumlin over in that drone footage I showed you. Cool. All right. So now there's multiple pages of questions. And yes, although I'm not here, I want you to try them and try them intensely. We got to work towards a test later this week. I'll stop babbling at you here, but give me a good effort. And yeah, you can use a partner if you want to go through that. If you make it through that in the single period, that's probably going to be about it. In the double, I'm going to give you a couple more jobs that are written on the big whiteboard over there on the side. And sorry I had to leave for the appointment. I'll see you tomorrow and hope you're all doing well. So long for now.